and represented by the symbol like phi. Null, the empty set, is the unique set that contains no elements whatsoever. Like this is the symbol, it means there is the null or empty set. So no matter the domain of discourse, we have the axiom like this, where x belongs to this symbol like phi. Here S is the subset of T. S is the subset of T means that every element of S is also an element of T. So S is the subset of T, and for all x such as belongs to S, and which implies x belongs to T. Here phi belongs to S because this is the null set, and phi is here the subset of S, and S is the subset of S, and S and T is the subset of S. S is a superset of T, means T is a subset of S. Note, S is equal to T, S is a subset of T, and T is a subset of S, or S is the superset of T, means S is a subset of T, that is the symbol x belongs to S, which is x does not belongs to T, so S is not the subset of T. And using Venn diagram, we can understand the position of S and T. Here S is the subset of T because S is under T. The area covered by S means the elements of S are already in the elements of T. So here S is the subset of T. S is the proper subset of T, means that S is a subset of T, but similarly T is not the subset of S because here the elements of T and S are, some elements are common, but all the elements are not common because S is under T. So here you can see the blue areas, here the blue areas, all the elements lies in the blue areas are out of S. So here T is not the subset of S. For example, you can see 1 2 is the subset of 1 2 3 because here two elements 1 and 2 are here in the first set. So here we can say 1 2 is the subset of 1 2 3, and in the Venn diagram you can see S belongs to S is a subset of T, and this is the proper subset of T actually. Sets are the objects. The objects that are elements of a set may themselves be sets. For example, let S is equal to X, such as X is a subset of 1 2 3. S is equal to phi, comma 1, comma 2, comma 3, 1 2, comma 1 3, comma 2 3, comma 1 2 3. So note that 1 is not equal to the set 1, not equal to the set 1. So this is how the set works. Cardinality and finiteness. This is called the cardinality of S is a measure of how many different elements S has. For example, the element here phi is equal to 0, and here the set 1 2 3 is equal to 3. Same here, AB is equal to 2. So 1 2 3 4 5. Here 1 2 3 and 4 5 equals, we have to just fill. We say S is infinite, and if it is not finite. What are some infinite sets? We have already seen the power set operation. The power set PS of a set S is the set of subset of S. PS is equal to X, such as X is the subset of S. And here is the example, the power set P of AB is equal to phi A, B and AB. This is the representation of, you know, the set, like here and here. This and this are the subset of the P. So here the maximum possibility of the formation of sets here: A, first of all phi, then thereafter A, B, and for A and B also. Sometimes PS is written 2 to the power S. Note that for finite set PS, there will be total number of elements here, like 2 to the power S. It turns out that Pn is greater than n. There are different sizes of infinite sets, like in ordered n tuples. For n belongs to n, an ordered n tuple or a sequence of lengths n is written a1, a2, a3 up to n. The first element is a1, etc. There are like sets except that duplicate matter, and the other order makes a difference. Note 1 2 is not equal to 2 1, not equal to 2 1 1. Empty sequence, singlets, pairs, triples, quadruples, quintuples, and dot up to n tuples. Here the Cartesian products of sets. For sets AB, their Cartesian product A cross B, such as AB, A belongs to A, B belongs to B. For example, AB cross 1 2 is equal to, here A1 same A2 same B1 and same B2. We have to form the sets, the subsets, using the elements like here. The first element A multiplied by involved with 1, so A1, then A2, then B1, then B2. Note that for finite AB, A cross B equals A and B separately. Note that the Cartesian product is not commutative for all AB, such as A cross B equals B cross A. Extends to A1 cross A2 cross A3 up to AN. And this is the union operator. For sets AB, their union A union B is a set containing all elements that are either in A or V in B, or of course in both. Formally, for all A, B, such as A union B is equal to X, and X belongs to A and X belongs to B. Note that A union B contains all elements of A and it contains all the elements of B. For all AB, A union B is a superset of A. And A union B